Hey everybody, in a couple of days I'll be traveling to Australia for the Organization for Human Brain Mapping Conference. It's one of my favorites. It happens every year in a different city around the world, and this year it's going to be in Brisbane, Australia. Now, a couple days before the real conference starts, there's something called a brain hack where we talk about some different software packages and methods that may be of interest to people who have arrived early before the conference starts. And I'll be helping promote something called Neurodesk, which is developed by Stefan Bowman and his colleagues at the University of Queensland. In what follows the next 20 minutes or so, this is essentially what I'll be demonstrating as part of Brainhack. And this is a wrapper that uses FSL and TBSS tools to analyze a diffusion-weighted data set. So it assumes you might already be familiar with that, and this video also assumes that you've already installed Neurodesk and it works on your machine. If you don't have it installed yet, see the link down below for some video tutorials about how to download and install it and make sure it's working. So enjoy the tutorial, hope to see you at OHBM, don't be afraid to say hi, and I'll see you all very soon. For this tutorial, we're going to be cloning a GitHub repository from my webpage. So go to github.com/AndrewYan, go to repositories, and notice there's a new one called TBSS example. If you click on that, there's only one Jupyter Notebook here, which we're going to use to demonstrate how to use TBSS. Now, just copy and paste this here, open up Neurodesk. Okay, I'm assuming you already have it installed. If you don't have it installed, look in the link down below for steps on how to do that. I'm going to do all this in Neuro Desktop Storage. You can really do it wherever you want, and then click on GitHub and clone a repository. Okay, so here, download the repository, make sure to check that, then copy and paste that address that we had before, and click on clone. Okay, great. So now we have TBSS example. You can navigate to it by double-clicking there, and then double-clicking to open up this Jupyter Notebook. Very good. I'm going to expand it here, and we're only going to focus on this Jupyter environment. So remember, if we want to execute any block of code, a good shortcut is to hold down Shift and press Enter. So this cell, this block of code right here, which is really just markdown, it's not going to execute any code per se, we'll kick to the next block, which is just a note. And then we now get to actual code here, which will do something like return what the vendor and model name of your computer is. We're also going to install things like nibabble, matplotlib, nylearn, and install some packages as well. Okay, so the important part here is to now load both mrtrix and FSL. So notice here, and this is one of the advantages of something like Neurodesk, there are many different versions of FSL we can install. It's very quick, very flexible to toggle between them. And initially when I was making this tutorial, I was using the most recent version of FSL, which I think is 6.0.7.4, but one of the examples with, I believe, topup did not work, so I needed to switch to 6.0.3. So that demonstrates one of the powers of the flexibility of something like Neurodesk. All right, I'm going to leave it to you. Again, I'm going to be going pretty quickly through a lot of this. I'm not talking so much about the theory of diffusion or TBSS itself, really focusing more on the code here, but read the markdown cells and the explanatory text on your own time. This cell right here, this exclamation mark, it's worth mentioning what that is. This is going to use your Unix shell to execute something like FSL info. So this is simply testing whether we have the FSL libraries installed. FSL info is a very basic command. It's going to read a nifty file or any kind of neuroimaging file and return the header. So that's things like number of time points, dimensions of the image, and so on. The next part of the notebook will use something called datalad to download a data set from openneuro.org. Specifically, we're going to download a single subject subcon02. This might take you 2 or 3 minutes depending on your internet speed, but basically what happens, it uses datalad, it installs the entire repository from OpenNeuro, which has a unique identifier DS001226. And then after that, it goes into that directory and it uses datalad get to retrieve that specific subject, in this case subcon02. It will download all the data in that subject's folder, including anatomical data, diffusion data, and functional data. So we're going to fade out for a little bit, come back in a couple minutes when it has finished. Going to the next block of code here, you may need to update this chdir to include TBSS example to make sure that the path is set appropriately. Because remember, within TBSS example, we have that data set we downloaded along with all the subjects. So run that block of code, OS lister, show you things such as the diffusion data, bvals, bvex, and this block of code right here will make it a little bit more compact and move the longer form version of the bvec and bval files into sub02 ap.bvec, ap.bval, and so on. And just a quick note, AP stands for anterior to posterior phase encoding, PA for posterior to anterior phase encoding, which will be important later on. Remember that FSL info command we had before? We're going to run that again with this file right here, and this is going to return all the data in the header for that particular file. So for example, the dimensions in number of voxels in the XYZ dimensions, also dimension 4 is time, meaning that there are 102 volumes, and this right here, data type 4, means it is a 4-dimensional data set. And here are the values for each of those different dimensions. So it's a 2.5 by 2.5 by 2.5 millimeter voxel resolution. And then we also have 8.7 seconds between each volume acquisition. We're also going to check the bval and bvex files using this block of code here. Okay, this is using awk. Don't worry too much about awk if you don't know that much about it. It simply extracts certain columns from, say, the output of FSL info. So this gives us in compact form how many volumes are there, in which case we have 102. And we're just going to double check the number of volumes in that diffusion data set with the number of entries in the bvex and bvals file. They should match up, right? So we should have 102 entries in bval bvec corresponding to the number of volumes in our diffusion data set. If there's a discrepancy, probably this is some kind of issue back at the scan center, which you'll need to resolve on your own. But in most cases, this shouldn't be a problem. All right, now let's get to visualization, which is one of the really cool parts of these Jupyter Notebooks. We have so many different options. We can load things from, Matplotlib or NiView. So we're going to explore some of those options. So this block of code here, which you can alter as a template if you want to, is going to load this DWI file, this acquisition and anterior to posterior phase encoding. And then it's going to use some other code, including something called NIB, to load that NII image. And we're going to look at some specific volume indices and see what the image looks like for different bvals. Okay, this fig axes, plot subplots, is going to organize it into 3 columns and then also label them for things like, middle slice for each of these volumes. Okay. So let's execute that block of code. Just gives it a second, and you'll see for volume 0, which is essentially like a T2 weighted image, where there's no bval applied to it, you see one set of bvals applied to it, which I think is around 1,000, if my memory serves. And then for a bval of about 3,000, you can see that the data quality seems to deteriorate, but it's actually more sensitive to changes in diffusion. Okay, another way to view these images is through Nilearn, which also contains a plotting library. And this is going to be important for sometimes interactively viewing the data as well. Okay, so this block of code right here is going to use the plotting function. okay, that we have from the NiLearn library over here. So this opens up 3 orthogonal views. This is my anterior to posterior phase encoding. And if you focus in on the very front of the brain, you can see how it's more deformed. It's as though there's a strong headwind, so to speak. It's deforming this part of the brain. It's more smushed in, and the back of the brain is a little bit more elongated. Okay, so this is another visualization function you can call upon, plotting from NiLearn. So that's all to illustrate that we need something to undo these warping issues. And the best way to do that is a command within TBSS called topup. All right. So this block of code is going to extract one volume, the first volume, from both the A to P and P to A data sets. Okay, so those are essentially the higher data quality, higher resolution, T2 weighted images without any B-vals applied yet. We're going to merge them together into a single data set. Okay, so this is going to have 2 volumes, just that first volume from AP and the first volume from PA. And this block of code is going to toggle between both the AP and PA volumes. You can see how they have different kinds of distortions, especially in the PA volume. So this block of code is just going to flip between them, 1 per second. Do that several times just to give you a sense of what they look like. So again, I encourage you, if you have time later on, just go through these blocks of code, just try to unpack what, say, the display function is doing. This time sleep, for example, is going to flip between each plot every second. Okay. This block of code is something I've already calculated for you. These are going to calculate things like the echo time, for example, and then put it into a file called acparam.txt, and then save it into a file called acparam.txt. Okay, so execute that block of code. We're just going to check that it does indeed contain what we think it should have. Okay, so, and these triplets down here, 0, 1, 0, 1, 0, and 0, negative 1, 0, is basically just representing the phase encoding direction for the A to P, which is the first volume in my concatenated data set, and then the P to A volume as well. Now, once we have all of these, we're going to run this topup command, again, using this exclamation mark to escape to the shell and run topup from the shell. It's going to load this concatenated AP and PA data set and also the information in acparam to unwarp the distortions in my A to P image. Okay. This last thing, this config file, this is something that comes by default with FSL. It tends to work pretty well in most cases, so we don't try to change it. But just be aware, even though we haven't actually created this file, it's something that can still be found within the TBSS library. And then we're going to output this file as AP to PA topup. Now this is going to take a while, so I'm going to fade out and come back when it has finished. Once topup is finished, we're then going to apply it to unwarp the data using apply topup. So this takes a couple of minutes. Just wait for a little bit and come back when it has finished. Okay, when that's done, just to show you what the output is, don't worry too much about these details. You can find them more on the ebook, but the output is going to be this AP corrected image. So our unwarped anterior to posterior phase encoded diffusion image. So now we can check how it fixed those distortions by using this block of code here, similar to what we used above with the plotting command. So now here, what I'd recommend is navigating around, especially looking towards the front of the brain and comparing it with the previous distorted image, which you can see here. Okay, so if we look at, say, z equals around 30, right around there. You can see that before it was a little bit more smushed in, and here it's been more extended outwards. Okay. So moving on, another block of code showing some plotting before and after. So this will show you the warped and the unwarped. Let's give it a second to load up. Okay, so that's when it's distorted. Here's unwarped, distorted, unwarped, and it goes back and forth about 5 to 10 times. So notice especially this slice we're fixated on here shows, especially in these frontal regions, how the warping has been corrected. All right, so now we move on to the TBSS part of fitting tensors and calculating things like fractional anisotropy. So the first thing we need to do is create a brain mask to restrict our analysis to only those voxels that include the brain. So FSL ROI extracts the first image of our diffusion data set, and then BED is going to extract just those voxels belonging to the brain and create a mask from that. We can look at the resulting brain mask by, again, using plotting, and this will return a binary mask where it will be white voxels where the mask is included, and then everywhere else is non-brain. Okay, so this looks pretty good. And over here, again, just to give you more options for how you want to visualize this, this is using NeView, and nv.loadVolumes simply requires the path to the brain mask or whatever other volume you want to look at. Moving on to fitting the tensors, the first step of TBSS is DTI fit. Okay, so this is code that I've used that's generated from the FDT GUI. So this is essentially the same thing you would see in my ebook tutorial if you were to use the graphical user interface to point and click and fill in all of the necessary inputs. So here it requires the corrected data, some kind of output prefix, and then the mask, as well as the BVEX and BVALs. Okay, now we use the TBSS commands themselves. First, we create a directory called TBSS, and we're going to copy this DTI FA that was generated in the previous step into this TBS folder, and we're going to change directory so that now we are in that folder. So TBSS1 preproc just requires that DTI FA as an argument. It's going to take a few minutes. And this is going to do the first step, which will clean up the FA images by removing brighter voxels and placing them into a folder called FA once it is finished pre-processing. Okay, for me, that took about 2 minutes. And you can follow this if you want to outside of this Jupyter Notebook. But for now, we're just going to make sure we are within the TBSS directory and then run the next step, which is TBSS2 reg, which is going to register the data to MNI space, a template space, and calculate the warps needed for the transformations. This capital -T option simply indicates that we want to use the FA template, this default FA 1mm template that comes with the FSL library. So again, let's give it just a couple minutes here. Wait a little bit. And we'll come back when it's finished. Again, this took me maybe 2, maybe 3 minutes. The next step should be a little bit quicker. This is going to apply the warps and bring the fractional anisotropy data to MNI space. As you can see here, the -S option will create the files mean FA and mean FA skeleton, which will be important for visualization purposes. You can see that this mask and also upsampling the data is going to put it into standardized space. And the next block of code here, again, uses the plotting command to look at this mean FA value and plot it on a template brain. You can change the threshold here however you want to. You can make it a little bit higher if you want to restrict it to only the more strong values of FA, whatever you prefer. And then down here is some more code, which is going to use these directionally encoded maps to show you these FA values and their primary direction of diffusion. So again, remember, red is primarily left to right, so corpus callosum, no surprise there. Something like blue could be the internal capsule going from bottom to top, and green is going to encode the direction from back to front, which could be something like the superior longitudinal fasciculus. So there it is, just a sneak peek about what we're going to be doing. Of course, there's some other stuff as well. For example, I'll be comparing that to MR-Tricks using a similar Jupyter notebook. But the idea is you can use these Jupyter notebooks within Neurodesk to load whatever software you want to use. So if you like TBSS, use that. If you like something Python related like NiLearn or NiPipe, use that. If you like MR-Tricks, use that. Really, it doesn't restrict you. All it does is remove any kind of version conflicts or dependency issues that you might run into if you try to download everything individually onto your own machine. It makes things much easier. I hope it makes things a lot more convenient, saves you a lot of time, and I hope you check it out. So until next time, see you all. I'll be gone for the next week and a half in Australia. If you're there, awesome. Hope to see people's research, hope to see what's going on. It's going to be really cool. So see you next time.